Thank you so much for your nice introduction. I'm very honored to visit CIO and give a talk. The title of my talk is A Brief Introduction of Digital Image Correlation. From Beihang University, I traveled a lot, far away from China to here. So many of the audience may never been to China. So first I would like to talk something about China. China is located in East Asia. It is 1, 2, 3, 4, the most populous country in the world. Second, it is the second largest economy, just behind the United States. And it is the third largest country in the world. We are very proud of the rapid development in the last 40 years. And we have four great innovations. Let's look at it. Dockless sharing bicycle. You can use a mobile phone to open a bicycle in any street of Beijing and ride to the places and leave the bicycle at convenient places. The high-speed railway. China now has the largest high-speed railway in the world. It travels with a speed over 350 miles per hour. And we have a very popular online shopping. We can buy anything, food, products, commodities from markets online, and the delivery can quickly, very rapidly send the things to you. And we actually in Mexico, I'm not used to use cash to buy something. In China, we just use a mobile phone to buy everything. Mobile payment, China goes beyond the world. Okay, Beijing is the capital of China. It has 3,000 years of history as a city, and is one of the most popular capital cities in the world. And I think the population may be slightly larger than Mexico City. And in Beijing, we have 7 UNESCO World Heritage Sites and 91 universities, including the prestigious Tsinghua University and Peking University. These 2 universities, in recent years, are normally ranked as top 30 in the world. And in Beijing, we have both modern and traditional construction buildings. This is a tall building in CBD of Beijing, and this is the National Stadium, the opening and closing ceremony of 2008 Olympic Games was held in these places. This is the Beijing, the National Center for the Performing Arts. There are some very old buildings, such as the Tiananmen Square, the Temple of Heaven, the famous Great Wall, one of the 7 miracles of the world. Our university, Beihang University, abbreviated as BUA because the former name of our university is Beijing University of Aeronautics and Astronautics. It's located in northern Beijing. You can see from this map, Beijing have 2nd wing, 3rd wing, 4th wing, 5th wing, and to 7th wing. Beihang is located between the 3rd and 4th wing of Beijing. These 2 figures shows the main gate of our university, and this is the new main building of our university. It was established 15 years ago, and was at that time the biggest single building in the campus of Asian universities. My university was founded on 1952. It's one of the 10 highest ranking engineering university in China. And it also well known as the cradle of Chinese aerospace engineering. We have over 2,000 faculties and 30,000 students. Half of them were graduate students. Our university is also one of the top 7 top institutes that are responsible for cultivating intelligence of military or technology. This picture shows an advanced remote long-haul unmanned aerial vehicle developed by a group in our university. This picture shows it was passing through the Tiananmen Square on the military parade conducted 3 years ago. This picture shows the so-called Lunar Palace 1. The Lunar Palace 1 was designed to test a closed ecological system to supply life for the members. And this picture was selected by Lecture as the best science images of the year in 2017. Okay, now move on to my field of research. I'm in the field of experimental mechanics. So, you know, the father of modern physics, Galileo, has a very famous quote: measure what is measurable and make measurable what is not so. The first sentence means that we should connect more physical quantities in an experiment as much as possible. And the second indicates that if the physical quantities cannot be measured, we should develop new or advanced techniques to measure these results. So you can see this picture. It is one of the picture in this famous book, Dialogues Concerning Two New Sciences. We were told in classes that the fully comprehensive understanding the bending strength distribution in the beam has spent almost over 300 years. But I think if we can measure the displacement and the strain distributions on the surface of a cantilever beam, it would be very easy to determine the stress distributions, because we know that stress-strain has a very simple relationship. So in mechanics, in solid mechanics, accurate measurement of displacement strains of materials and components structures subject to external loading are of key importance. In solid mechanics, we have several sub-branches. One is so-called computational mechanics. We use now the finite element method is very well developed. Using FEM analysis, we can determine the stress distributions, strain distributions within a material structure component. So it is very powerful. It can deliver full-field 3D results. So, however, in the field of experiments, the technique for measuring displacement and strain has remained unchanged for a long time. In engineering field, we use strain gauges, displacement sensors, accelerometers to measure strain, displacement, acceleration at a single point along a single direction in a contact manner. So for a long time, experimental mechanics was considered as a poor relative of computational mechanics because the techniques for measuring displacement streams is very limited and cumbersome. But now this situation has been changing. About 30 years ago, the scientists in our field has introduced various optical techniques for full-field, long-contact deformation measurements. These optical techniques can be classified into two categories. The first is interferometric techniques. We use coherent light, for example, a laser source. The laser source we use laser source to illuminate the test sample surface. The reflected, diffracted, or scattered coherent wave was received by a camera and we can have fringe patterns. The fringe patterns has a relationship with the desired displacements or streams. Also, frankly speaking, interferometric techniques has evident advantages. For example, they can offer high sensitive measurements with an accuracy higher than several hundred nanometers or even higher. Also, the measurement was very straightforward. We can observe the intensity of stress or displaced stream by viewing the distribution or the density of the fringe patterns. But it also has several disadvantages. For example, it must use a laser source, so it has a complicated setup, different mirrors, lenses, and it is very sensitive to ambient vibrations. All the measurements must be performed on a vibration-proof platform. We also need complicated fringe processing and phasor analysis to extract phasor information from the fringe patterns. All these shortcomings limited the use of interferometric techniques in laboratory applications. It cannot be used in an outdoor environment. We also introduced non-interferometric techniques to experimental mechanics. The typical non-interferometric technique is called digital image correlation. We just record the images at different states and compare these images to get the desired kinematics field. So compared with interferometric current patterns, the image-based optics has evident merits. For example, it is a simple setup, easy interpretation, it is robust against ambient vibrations. It has a much wider range of applicability in scientific research, engineering, and industrial applications. So, what is digital image correlation? One sentence definition. Digital image correlation, in my own personal opinion, is an image-based optical method for extracting accurate motions in digital images. Recently, I published a review paper. In that review paper, I gave my definition, more accurate definition of DAC. DAC refers to long-contacting image-based method for shape and deformation measurements. The measurement of DAC can be divided into three steps. First, we acquire the images before and after deformation using digital imaging devices, typically digital camera. We also can use electronic imaging scaling probe imaging facilities such as SEM, AFM, for example. After recording these images can be processed using correlation-based matching algorithms to quantitatively extract full-field displacement. However, the displacement is noisy, so to get the more important value, strings, we should use proper numerical diffusion algorithms to estimate the full-field strain responses. Digital image correlation can be divided into two words. One is digital imaging, the other is correlation. So for different types of DAC techniques, the single camera DAC 2D and the two camera stereo DAC and the volumetric digital image correlation. The first step is to record digital images of a test sample surface or the volumetric images. However, we not only capture images, we also establish a coding system and assume a fixed image model. The second step is comparing the images recorded at different states using correlation. Correlation is actually a similarity measure to find the similar subsets or template in different images to register the same physical points. DAC can also be, from the photomechanics perspective, DAC can also be integrated bouncing in the center of the stage of experiment, because currently DAC is more popular than other optical techniques. There is SPI, digital holography, shotography, and marine interferometry. As for me, digital image correlation has a special meaning. I have been doing DAC continuously for over 15 years, and I have published over 100 papers and given 8 plenary talks or keynote talks in different conferences. I was being given the prestigious Plantain Award last year by Society of Experimental Mechanics in the United States, and was given the top cited author award this year by Institute of Physics UK. And so what can DAC do? The first thing DAC can deliver is measurement, to measure displacement, strain, or shape. Also, but shape can be measured by more conveniently or more powerfully by other techniques such as fringe projection. So the main purpose of DAC is to measure displacement strain. We can measure surface or interior displacement and strain at various spatial and temporal scales under various conditions. Based on the measured displacement and strain fields, we can identify the mechanical properties of a test object. These mechanical parameters include Young's modulus, Poisson's ratio, elongation at break, R value, ceiling limit, residual stress, stress intensity factor, coefficient of thermal expansion. This figure shows the strain curve measured by digital image correlation. And also we can use the result obtained by DAC to validate the correctness of finite element simulation and theoretical predictions. These two figures shows the setup of 2D and 3D DAC. 2D DAC you can see use a single camera, but it is limited to in-plane measurements of planar objects. So to extend the applicability and the improve accuracy of 2D DAC, 3D DAC using two cameras, just like it is also known as binocular stereo vision. It can measure shape and deformation of arbitrary surfaces, so it has a wide applicability. We also can use the volumetric images acquired by X-ray CT or even synchrotron CT to capture, record the volumetric images of an object at different states. And also using correlation analysis, we can extract the truly internal displacement of strain field of a test object. This figure shows the 3D dimension in the lithium-ion battery electrode. And this figure shows this strain field close to a 3D crack within an object. So the implementation of DAC is very simple. It can be divided 3 steps. The first is image acquisition. We should apply random speckle patterns by just developed paintings on the test sample surface to generate a random intensity distribution. And then we record the digital images using digital imaging devices. Then we perform correlation analysis to extract a displacement field. Then we use numerical differentiation to get the strain distributions. You can see the implementation of this is very simple and straightforward. But why this technique has been researched over 30 years, and now a very hot topic in our field. It is because the secret of DAC lies in details. There are many details involved in different steps of its implementation. For example, let's see the simplest 2D DAC. It uses a single camera, a planar sample, and we can see that there are many details. For example, the illumination light may vary. The intensity of the illumination, the ambient light may vary during image capture. Theoretically speaking, we want the optical axis of the camera should be aligned perpendicular to the test sample surface. But in practical cases, the angle may be not exactly 90 degrees. It may be oblique. As we just mentioned, we should decorate speckle patterns on the test sample surface. Different people using different techniques may generate different speckle patterns with different intensity distributions. So we can see that there is no the same speckle pattern in the world. So what is the effect of speckle pattern on final DAC measurements, and how to fabricate a good speckle pattern? These questions are very important. For 2D DAC, out-of-plane motion is very dangerous because out-of-plane motion changes the object distance of the imaging system and will introduce additional virtual displacement. This virtual displacement can be understood as displacement errors. For a real lens distortion is unavoidable. Lens distortion changes the original assumed linear relationship between image motion and object distance. So how to quantify this distortion and remove the influence due to this distortion. For a digital camera, we also find that the images are noisy. Also, we found after power on the camera, the temperature inside the camera will increase about 10 Celsius degree. In field measurements, in outdoor measurements, ambient temperatures also changes. We found that these slight temperature changes in digital cameras can induce strain, virtual strain, and virtual displacement. For correlation analysis, we should input a lot of parameters, such as the size of the template, how to choose a robust, also efficient correlation function, and the template not only displaced, it also may be strained after deformation. So we should consider the practical deformation within the target templates. So we should, in DIC, we want to get full field displacement. There are maybe meaning calculation points. So how to calculate these points? Raw or other methods. So this is a question. We know that the minimal resolution of a digital image is a pixel, but the resolution of 1 pixel is not enough. We should get subpixel accuracy. So subpixel registration algorithm has been considered as a key technique in DIC. In subpixel registration algorithm, there are also many details. So, such as initial gaze, intensity, interpolation, convergence criteria, for example. So now, in my opinion, DIC measurement actually has a long, complex error chain. If we realize DIC measurement is an error chain, there is a big leap in the understanding of DIC technique. Okay, why do we use DIC? Because it brings us a lot of advantages in measurements. The first advantage is non-contact full field measurements. This in contrast to conventional experimental techniques, point-wise contact method. The second is it is very simple. It has a simple setup because we just capture images using digital cameras. And so the implementation is very simple. And it is, since we don't use a laser source, so it is robust against ambient vibrations and ambient light variations. And most importantly, it has wide applicability. It can measure both planar curved surface to truly internal measurements. It can measure from very small strain to as much as 500% large deformation. It can measure deformation from nano microscale to macroscopic or even kilometers scale. It can measure deformation from room temperature to extreme high temperature environments, from static to high speed impact loading or even explosion. Compared with ESPI and marine fluorimetry, DIC can simultaneously yield 2D or 3D surface displacement vectors or strain fields. In different disciplines of science, there are similar techniques. For example, in experimental fluid mechanics, there is a sister technique called particle image velocity. Particle image PIV is very similar to DAC in principle and implementation, but it uses laser sources to a slight light to illuminate the fluid, and the particles should be added to the fluid, and use cameras to record the double exposure images. And it also uses quartz correlation. We can determine the motion of each particle. In biomedicine, computer vision, geophysics, there are a lot of techniques that has a similar principle to DAC. The basic algorithm used in all these techniques we call the image registration. But DAC is special, is different. Why? Because the test object in solid mechanics is solid materials or solid structures. The deformation is generally very small, cannot be discerned by naked eyes. So in DAC, accuracy and precision is always the first objective. To achieve high accuracy, high precision measurements, we use intensity-based matching rather than feature-based matching. We use spatial domain correlation rather than fixed dimension cross-correlation. We use artificial speckle pattern with active illumination rather than natural speckle pattern with a passive illumination. Okay, now I will talk about the historic development of DAC. In my recent review paper, I retrieved the number publications of 3 most widely used optical techniques in experimental mechanics: DAC, Moire interferometry, speckle pattern interferometry. And we found that we got this data from 2 different data sources. One is Google Scholar, and the second is Web of Science. Since Google Scholar incorporates more publications from different local languages, so the number of publications in Google Scholar is much higher than the number of publications in Web of Science. But these 2 data sources show the same trend. That is, during the first part, from 1982 to 2000, you can see that Moire interferometry SPI seems more popular than DAC. But after 2000, DAC experienced a rapid increase in publication. So according to this trend, I would like to divide the history of DAC into 2 phases. The first is the foundation nailing stage, and the second is the boom stage. Zoom was not built in a single day, so DAC is not done also in a single day. So what is the reason why we develop DAC? Let's start with a speckle pattern. We know speckle pattern is a random intensity pattern produced by using mutual interference of set of wavefronts. This phenomenon has been investigated by scientists since the time of Newton. But speckles has come into prominence since the invention of laser and has now found a variety of applications. I think as an audience should be very familiar with speckle patterns. We know that during the use of holography, speckle pattern is considered as a noise. So people try to find different ways to remove speckle pattern. However, there was a scientist in UK found speckle pattern was related to the microsurface structure of an object. So after this foundation, Dallas Gabor, Nobel Prize laureate, once said that the biggest innovation of holography lies in speckle pattern. So in experimental mechanics, we introduced about 40 years ago speckle pattern for metrology, for mechanical metrology. This is called speckle photography. We use photographic plate to record the laser speckle pattern at different states. This is called double exposure speckle pattern photography. The recorded photographic plate can be illuminated with a laser, and the two speckles just like two holes. So Young's fringes can be observed. The direction and the distance between the Young's fringes is related to the motion of the speckle pattern. So this is speckle pattern photography. However, with the scientists in our field find the speckle photography has several obvious limitations. First, it has limited measurement range. The measurement displacement should be larger than speckle size, otherwise double flow will not be generated. However, we cannot measure too large displacement, otherwise there will be a decorrelation, and we cannot also observe the Young's modulus or Young's fringe pattern, Young's interference. Also, using a photographic plate involves several difficulties, such as cumbersome, time-consuming, and inaccuracy. So it is natural to raise the question, can we realize digital measurement without using a photographic plate, using digital cameras? The two professors in America, University of South Carolina, Professor Peters and Russell, they published a paper in Optical Engineering in 1982. In this paper, they use image scanning. At that time, the definition of digital camera has not been developed. They use an image scanner rather than a photographic plate to record the laser speckle patterns at different states. And they use correlation to analyze the two images to get image displacement. This is a groundbreaking work. It has been cited over 1,600 times in Google Scholar, and ranks second among all the papers published regarding DIC. However, if you read this paper carefully, you find this is a simple idea. And the algorithm used in this work is very crude. They use laser illumination. They use the simplest cross correlation. They only consider translation, does not consider straight rotation. And they can only determine displacement with integer accuracy. Later, in the same group, there is, at that time, there is a Professor Michael Sutton was an associate professor. Now he was known as the most people in our field. 1 year later, he published a paper in image and vision computing and made significant improvements to DIC. He no longer used laser illumination. he used white light. He used a more convenient sum or squared difference correlation criteria. He not only considered displacement, also considered strain and rotation of the template in deformed images. He can achieve subpixel accuracy using bilinear interpolation. This paper has been also been cited a lot of times. In 1985, Michael Sutton wrote a short review paper. In that review paper, he summarized the important improvements he made to DAC and demonstrated the accuracy and practicality of DAC at that time. This paper has been cited over 1,800 times and ranks first among all DAC papers. And in 1989, Michael Sutton and his master student Hugh Bragg published a paper in experimental mechanics. They put forward the classic Lieder-Vogts algorithm for accurate subpixel detection. During this stage, Michael Sutton and his colleagues also developed a simple stereo vision system, and they verified the ability to make a strain measurement in cracked material. This was the first paper regarding 3D DAC. And in 1999, Professor Bay, he was also a professor in the United States. He was in the field of biomechanics. He used X-ray CT to scan the vertical images of a tropical bone and extend the 2D method to volumetric images. And but however, this technique requires a tomographic imaging facility, a CT, and limited to those materials providing sufficient contrast during tomographic imaging. This paper was the first paper regarding DVC. During the foundation learning stage, the pioneers of our field laid the framework and the foundation of DAC techniques. And also in this stage, we found that over 90% of the papers were published by the scholars from the United States. However, in that stage, the DIC algorithm details were not fully understood, and the error chain was not recognized. Also, at that time, digital camera and computer is very expensive, but with a low performance. So these disadvantage conditions lead to large error, poor readability, and low efficiency, limited applications of DAC. During the second stage, boom stage, based on the pioneers of the first stage, we also made some significant improvements in DAC theory. For example, Dr. Sun in Nanyang Technological University in Singapore, Professor Hill in France, they proposed a global DAC using finite element analysis. And as for me, I proposed a lower reliability guided digital integration and also developed advanced high efficiency, high accuracy new subpixel registry algorithm. This algorithm has overperformed the classic Lieder-Vogts algorithm and has now been used as a standard DAC algorithm in our field. Professor Otto, also Professor Katia, developed single canvas DAC, panoramic DAC. Many research workers in the second stage dedicated to the understanding, quantification, and elimination of errors associated with various details involved in the complex error chain. So, in short, the research in our field is dedicated to develop DAC techniques with a fast computational speed, with a more accurate, robust practical measurements. And in the second stage, the scholars for all around the world, not only limited in the United States, contribute a lot to this technique. We developed new and better DAC algorithms and combined DAC with various imaging devices such as optical microscope, SEM, AFM, high-speed digital cameras, fluorescent optical microscopes. We want to understand and eliminate the errors involved in DAC measurement. We used DAC to different disciplines, not only limited to experimental mechanics, but to civil engineering, material science, biomechanics, aerospace, for example. In 10 years ago, in 2008, when I was a postdoctor in Nanyang Technology University, I was encouraged to write a review paper. This review paper has been selected as a cover story of Bachelor of Science Technology. And in this review paper, I reviewed the methodologies of 3D DAC and measures for achieving high accuracy DAC measurement were also recommended. If you are interested in DAC text, you can read this paper. This paper has been downloaded more than 34,000 times and get a lot of citation. Since this review paper was very popular in our community, I was invited to write an updated review the year before last year. The editorial board of Beijing Science and Technology wrote an email to me and told me my previous review paper was very popular with readers since its publication. But they haven't published another review paper on this topic. So he invited me to write a new review paper and give me a small honorarium. After 1 year and a half year hard working, I finally published an updated review paper in the same journal. This review paper entitled DAC for Surface Deformation Measurement, Historical Developments, Recent Advances, and Future Goals. In this updated review paper, I reviewed important advances made to DAC since after the first review paper, and also some further improvements that are needed and further goals in this field are also discussed. I was also invited by Professor Pramod Rostich, one of the chief editor of Optical Analysis Engineering, to write a book chapter for his book, Digital Optical Measurement Techniques and Applications. This chapter has over 60 pages and gave a lot of algorithm details about DAC. Finally, I would introduce some equipments developed in my laboratory. This is the advanced video deflectometer. This equipment was developed to measure vertical displacement of large engineering structures, such as bridges. You know, bridges generally cross over rivers, valleys, so the deflection of a bridge is generally very difficult to measure. Based on off-axis digital image correlation. So in using this system, the optical axis is no longer perpendicular to the test sample surface. So we must develop some new or advanced calibration techniques. Here is a video showing the measurement of ridge deflection during the train passing by. We can realize real-time, accurate deflection measurement at a frame rate over 100 frames per second. This paper has been published in DT&E, was a record of the first among all the papers published in that journal. We also established an advanced video extensometer. You know, what video extensometer is a very simple and straightforward concept. We just, there are some commercial companies selling video extensometer, but I found that unfortunately the results obtained by commercial products are not accurate enough, because these companies, the engineers in these companies are not in the field of DNC. They cannot understand the error chain involved in imaging. So I developed an advanced video extensometer. It can deliver very accurate, real-time strain measurement during the actual tensile testing. There are two innovations in this equipment. One is we use a high accuracy bilateral tape-centric lens. This lens is very expensive, but it can offer an evident advantage. The magnification factor remains constant during, even if out-of-plane motion occurs to the test sample. This video shows the measurement, strain measurement during tensile setting. You can see that before loading, all the strains fluctuates around the zeros. But if actual load is applied to the test sample, the actual strain and the transfer strain can be very accurately measured. We repeat this measurement 3 times, and the repeatedly is very good. When I was entered Beihang University 9 years ago, one of my colleagues want to collaborate with me to measure the strain deformation of hypersonic vehicle materials and structures. Hypersonic vehicles can fly at a speed over 5 Machs. So during high-speed flight, there is a serious friction between the air and the thermal protection system. So the thermal protection system, the temperature will be very high, even higher than maybe in the worst case over 2000 Celsius degree. So the reliability and the safety of the TPS system plays a vital importance in the development of hypersonic vehicles. In ground testing, we must perform a lot of tests to test the performance of the TPS system. We use infrared heating based on quartz lamps. We also use high-speed wind tunnels, high-temperature wind tunnels. Here is the infrared heating system developed in Beihang University. We place the sample here or here and heat the sample from the back side and measure the deformation, high temperature on the front side. But unfortunately, At our first initial experiments, we found that there was a serious decorrelation effect occurs. Because when the temperature of the test object exceeds 500 Celsius degree, it will eliminate very serious thermal radiation. The thermal radiation will corrupt the originally reflected light, so the recorded images tends to be saturated and no longer impressed by DAC algorithm. So thermal radiation induced speckle decorrelation is the first challenge. The challenge is in high temperature DAC measurement. To overcome this challenge, we developed a novel active imaging DAC system, which is insensitive to thermal radiation. Actually, this system is very simple but very exciting. The key innovation in this system is use monochromatic illumination instead of white illumination, and we will add a bandpass field just before the lens. And in this way, we only allow the actively illuminate wave to enter the camera sensors. Thus, thermal radiation can be excluded. Using this active imaging DAC system, we can acquire high contrast, very good images at over 1,200 Celsius degrees. This paper was published also in MSD, has been cited over 150 times. That's first among all papers regarding high temperature testing. In last year, we conducted several experiments in high temperature winter tunnel, and we measured the head part of our high-speed missiles. In high-speed winter tunnel, thermal radiation is more serious, so we use UV DAC, ultraviolet DAC, to overcome thermal radiation and achieve a shape measurement at over 1800 Celsius degrees. These are the results we obtained for the ablation tests, and we can measure, reconstruct the shape during different states. And these experiments provide very important information for reliable design of hypersonic vehicle materials. Okay, that's all my talk. Thank you so much.
We have time for a few questions. Please, you have some, please.
I'm sorry for English.
Preguntas, alguno que si quieren en español y podemos traducir.
How to get the spectrum on the grids?
How to apply the speckle on what?
On the grids.
In bridge deflection measurement, we're using natural textures rather than spot pattern. But at sometimes, if we want to make a bridge deflection at light, we can attach LED lights on the bridge, and that's very effective. Thank you.
¿Alguno más? Okay, I have a question. It's about measurements. Basically, with your techniques, you can measure in plane, isn't it? So, in out of plane, perhaps you need stereo.
Yeah.
So the sensitivity is not the same, basically. Or is it the same? You can go to nanometers with the in plane. But what about out of plane measurements?
That's a good question. For in-plane measurements, the accuracy, now we can achieve accuracy exceeding 0.005 pixels. But for stereo DAC, maybe we can achieve the similar accuracy for in-plane measurements. But for out-of-plane measurements, the accuracy is slightly lower, decreased. It depends on the configuration of the two cameras.
Second question is you told us that the Newton-Raphson is the method that you.
That's the method, yeah.
It was the most used method for going to sub-pixel accuracy.
Yeah.
Is it still the most used now?
I give this. I gave a talk in ISOT in Cancun, and in that talk, I give detailed comparison between Newton-Raphson algorithm and the inverse composition of Gauss-Newton algorithm I proposed several years ago. And the ICGN for short, this algorithm, ICGN algorithm, is more efficient and more, it's more efficient and theoretically speaking, Newton-Raphson algorithm is equivalent to ICGN algorithm. But ICGN algorithm has two advantages. One is it eliminated several redundant calculations involved in Newton-Raphson, so it is more computational efficient. Second, during the implementation of the new algorithm, ICGN, it involves the calculation of this intensity gradients of reference images. We can use a special field. So, ICGN algorithm offers better noise robustness performance. So now ICGN, in our field, all the guys think ICGN is better than Newton-Raphson. I published that paper in Experimental CAT. If you are interested, you can.
Okay, any other question?
I would like to know if the Moire interferometry is popular today or no.
Oh, I think it is not popular. My supervisor, postdoc, PhD supervisor in Tsinghua University, Professor Huiming Xie, and his supervisor, Professor, the pioneer in Moire interferometry is Daniels. Daniels is in which university? The United States, in Virginia University, or in technology, Virginia Institute of Technology. My supervisor has worked with Professor Daniel Post 30 years ago in ICS. But now in China, my supervisor, maybe published a paper about Moire interferometry every 2 years or 3 years. He also uses DAC. The fabrication of high sensitivity gradients on a test sample is very, very cumbersome.
Thank you.
Okay. Any other question? Everything? Well, we thank you very much.
It's my pleasure.